Hi, today we're going to look at titrations, and earlier in the year we looked at titrations of strong acid and strong base, and what we're going to do today, we're going to look at, in addition, titration of a weak acid plus a strong base, or weak base plus a strong acid. When you have a strong acid and a strong base, you get what's called a neutralization reaction occurring. And we use indicators to help us determine if that neutralization has occurred. Earlier in the year, we used phenolphthalein as our indicator, and that turned that bright pink-purple color. The observable point where it changes color is called the endpoint. So when it turned that pink color, that was the endpoint. The endpoint and the equivalence point are not always the same, as we saw during that lab. The equivalence point is when you have exactly equal moles of your acid and base, and that can be slightly different from your endpoint. If you choose an indicator that changes pH near the equivalence point, then it will be a proper indicator to use for the reaction. So the equivalence point is the point where there are equal moles of your acid and base. If we're doing a strong acid and a strong base, then the pH, the equivalence point, would be 7. If we're doing weak plus strong, it will not be at 7. For all of these reactions, we're assuming that it's at 25 degrees Celsius. Remember, when temperature changes, K changes, so temperature is important here. Okay, so when you have a strong acid and strong base, you get what I call that really sharp S curve. And so it's going to look something like this. So it's going to start low if you have a strong acid. It's not going to start very low. So maybe a pH of 1. And very little happened, as we saw when we were doing that titration. It barely was going up. And a lot of that increase was due just to changes in dilution. Once we had excess OH, that pH shot up and went straight up. And then eventually, if we kept adding the sodium hydroxide, it leveled out again. So kind of looks like this sharp S. Right at the middle of that rapid increase, this is where we get our equivalence point. And if we're doing a strong acid and strong base, that equivalence point is at a pH of 7. So right at the middle is our equivalence point. A strong acid and strong base, that's going to be at 7. All right, so if we have a strong acid and strong base, we can do some calculations, and we can look at the balanced chemical equation to see what's present at that equivalence point. So if I have 1 mole of HCl, which is a strong acid, and I have 1 mole of sodium hydroxide, which is a strong base, the limiting number of moles is 1. So 1 mole is the limiting. They're both limiting. And so they're completely used up. And NaCl is formed. How much NaCl? 1 mole of NaCl is formed. Okay, so we don't have any of this left over. They're all equally reacted. So at the equivalence point, we have 1 mole of Na plus, and we have 1 mole of Cl minus. These are both neutral ions. They have no effect on the pH, and so the pH will be 7. Okay, if we have the same chemical reaction, and half of the HCl has been titrated. So if we have 1 mole of this and half of it has been titrated, then we're left with a half mole remaining. If I used up a half mole, of NaOH. So if a half mole was provided and that half mole completely reacted with the HCl, then we don't have any of this left. And if it's halfway to the equivalence point and a half mole of this is remaining, that means a half mole of this reacted. And because a half mole is the limiting, that means we had a half mole formed of the salt, which has no effect on the pH. So we have a half mole of HCl remaining, which tells us we have a half mole of H plus. Because this completely dissociates, because it's a strong acid, you also have a half mole of the Cl minus remaining. And then on the product side, we have a half mole of Na plus that has formed and a half mole of Cl minus. So if we're going to put these in order of our species, a lot of times I'll ask you which species are present and to compare them. And so we have 1 mole of Cl minus total. And then we have half mole of H plus. And then we have a half mole of Na plus. So all I did here was just combine the Cl minus. And so because the Cl minus and the Na plus have no effect on pH, this is going to result in an acidic pH because we have leftover hydrochloric acid. Right, if we have a weak acid and a strong base, our curve is going to look a little bit different. And that's because we have this buffering region. And so if I start off with a weak acid, let's say it starts off at like 2.5 or 3, there's this buffering zone where it goes up, but just slightly. And then all of a sudden it shoots up just like it would in a strong acid, strong base titration. And the end of the curve is always the same. It doesn't matter if it's a strong acid, strong base, or weak acid, strong base. As long as you have excess OH at the end of the reaction, the end of the curve is going to look the same. And so this right here we call the buffering region. It's starting to go up, but you have some of your weak acid and some of the conjugate base present. And so as a result, you have a buffer present. So right at the middle of this where it shoots up, this is going to be the pH at your equivalence point. So if I'm doing a weak acid and a strong base, if this is 7, I would expect my equivalence point to be higher than 7. So I'm just making this up, but let's say 8.5. Okay, so we have this excess weak acid as we're adding the sodium hydroxide, our strong base. So we have the excess weak acid, and that's why we have the slight increase in pH. It's becoming less acidic. And we have the conjugate base forming. The conjugate base is weak, and so that's why we don't have this big increase in pH until we have excess OH. That's where we get this dramatic portion right here. Okay, so what we have, this is an example of a weak acid, strong base. And so if I'm given a mole of this and I'm given a mole of this, our limiting mole is 1. So these are completely reacted with each other at the equivalence point. And then we have 1 mole of our sodium acetate formed. Now this is not a neutral salt. The Na plus is a neutral ion, but this is a basic ion. This is a basic anion. If you put this into water, it's going to produce OH minus, and so it's basic. So we have 1 mole of this formed. This is a spectator ion, so we could say we have 1 mole of Na plus at the equivalence point and 1 mole of our CH3COO minus. All right, if we have the same reaction and only half of the weak acid has been titrated, so if I have 1 mole of this, if half of it has been titrated, I have a half mole of acetic acid left over, unreacted. Okay, so if I was starting off with a half mole of NaOH and I completely reacted the NaOH with the acetic acid, that leaves me with 0. And the sodium acetate forms, how much forms? Well, it's based upon the limiting, which is a half mole. So we have a half mole of this formed. Okay, so at halfway to the equivalence point, we have this weak acid and its conjugate base. So we have a buffer. As soon as we start adding this NaOH, this is an induced buffer. As soon as we add the NaOH, we have some of this conjugate forming. And as long as you have some of this weak acid left over, we have a buffer present. And so what happens with the weak acid? Well, most of it stays together. There is a very small, less than 5%, very small percent that ionizes. So most of this stays together as HCH3COO, so about half mole, approximately. You're going to get a teeny tiny amount of H plus and CH3COO. This is going to be a very small amount. Because most of the acetic acid stays together because it's a weak acid. It has a low Ka. It does not form product to a large extent. Okay, this is a ionic compound that's in water, so this is going to completely break up. So we're going to have a half mole of the Na plus, and we're going to have a half mole of CH3COO. So what species are present at halfway to the equivalence point? At halfway to the equivalence point, we have a little over a half mole, so I'll put a little plus here, of CH3COO, acetate ion. And then we have a half mole, exactly, of Na plus. And we have a little bit less than half a mole because some of this acetic acid dissociates. So 0.5 mole minus, slightly less than half a mole of HCH3COO. And then we have a very teeny tiny amount of the H plus. Very small amount. Okay, so if we wanted to look at our species, this is what we have. Okay, this walks through the process of how to do a titration problem. And I'm going to walk you through one so you can see what that looks like. So here we have, this is a weak acid. So we have HCN, a weak acid, and NaOH, a strong base. So I'm going to go ahead and write out my balanced chemical equation. This is hydrocyanic acid plus sodium hydroxide. It's going to make water plus sodium cyanide. And if we were to balance this, it's all 1 to 1 to 1 to 1. All right, so this is what I have that goes with the HCN, and I have 0.016 liters of the HCN. I have 0.0320 molar, and remember, liters times molarity equals moles. Okay, so I'm going to find out how many moles of this acid I have. And when I do that, I get 0.000512 moles. That's how much I'm provided with. Now, if I'm going to go to the equivalence point, that means the moles of the acid will equal the moles of the base. So these will equal each other at the equivalence point. And that means they're going to get completely reacted with each other. They're going to completely react with one another. Okay, so they completely react. They're both the limiting reactant. And then we get some NaCN formed. How much of the NaCN is formed? 0.000512 moles are formed. We want to find pH. And in order to find pH, we need to know our H plus or our OH minus. When I look at this product here, the Na has no effect on the pH, but the Cn minus is a basic cation or anion. And because it's a basic anion, it's going to result in a pH greater than 7. And because it's a basic anion, we're going to need to find the amount of OH produced by this basic anion. And when we do that, we need to know the concentration. Here at this point in time, we know moles, but we need to know the liters because we need to know the molarity. And because we've taken two different solutions, you don't need to draw this part, but if I throw some HCN in here, and then I throw some NaOH into the same beaker, we need to take into account the total volume because volume affects the concentration. It can be more concentrated or more dilute. So we need to know the total liters of solution. SOLN. Okay, so how do I find the total liters of solution? Well, I know the liters of HCN that was provided to me. What do I know about the NaOH? I know the moles of NaOH, and I know the concentration of NaOH. Okay, there's a couple different ways that you could go about this, finding the X liters of NaOH. We know molarity equals moles per liter. And the molarity is 1.024. That's provided to you right here. We know the moles because it equaled the moles of HCN because it's at the equivalence point. Equivalence point is equal moles. Okay, so we can use the molarity of the NaOH, the moles of NaOH, find the liters of NaOH. We can do the Thomson switch. And when I do that, I get 0.0005 liters. Okay, that's one way you can do it. Okay, another method you can use is you can use MV equals MV. As long as we have a 1-to-1 ratio, we can take our liters times our molarity equals our molarity times our liters. And from there, you can solve for your second volume. So whatever makes more sense for you. But either way, in the end, you need to know both the volume of the HCN that was added, and you need to know the volume of the NaOH. You need to have total liters. And my total liters is 0.0165. And when I take my moles divided by my liters, this is going to give me my concentration of my CN minus. This gives me a concentration of 0.031 molar CN minus. This is my conjugate base. HCN is my weak acid. CN minus is the conjugate base. All right, this is a base. And this is a 1 right here. Because this is a base, I need a KB. Okay, I need a KB because I'm going to use my shortcut. At this point in time, essentially this is a salt problem. This is a basic salt at this point. And so we're going to solve it like we would any other salt problem. Because it's a basic salt, we use the KB. KB equals x squared over the molarity minus x. Okay, we can do it that way. We could also write out an ice table if we really wanted to. I'll just show you what that would look like. Okay, so this would be our CN minus molarity. This is water, and this is minus X. These are products, so they're 0 plus X. So this is X at equilibrium. This is X at equilibrium, and that's how we get this right here. So KB equals products X times X, so X squared, over the molarity minus the X. And in this case, the molarity is 0.031. So this is what my ice table would look like. All right, before I solve for X, and we saw in that ice table that X is going to be your OH minus. That's what we saw in that ice table. And because of that, I need a KB. So I need to look at my table on my gold sheet and find the Ka for HCN. Why? Because the Ka for HCN times the Kb for my CN minus equals my Kw. So the Ka for HCN is 7, let's see, where is this? Oh, no, I lied, 6.2 times 10 to the negative 10. So I can take this times my Kb. That's going to give me my Kw, which is 1 times 10 to the negative 14. So my Kb is, for CN minus, is 1.61 times 10 to the negative 5. Okay, now I can plug this into this formula right here. 1.61 times 10 to the negative 5 equals x squared over my molarity, which is 0.031. Now in this case, I don't know x, so I can ignore x, and I can solve for x. And when I solve for x, this is a very long problem, I get 7.07 times 10 to the negative 4. X is because this is a base, is my OH minus. And so my POH is the negative log of my OH minus. And so my POH is the negative log of 7.07 times 10 to the negative 4. My POH is 3.15. pH and POH add up to equal 14. So 14 minus 3.15 gives me a pH of 10.85. Really long problem. So this is the process. Write your balanced chemical equation. Find moles from what's provided. Once you find the moles, find the liters of the other substance to get your total liters. The moles, the limiting moles, that's how much of your conjugate will form. So using your moles divided by the total volume of your acid and base, that's going to give you the concentration. Once you have the concentration, figure out whether you're looking at an acidic salt or basic salt. If it's a basic salt, you're going to use your Kb and you're going to solve for X. Your X will be your OH minus. From there, find your POH and then your pH. Okay, number 2. Okay, this one's slightly different because we have a weak base being used instead of a weak acid. So we're going to still start the same way. So we have hydrochloric acid plus ammonia. Acids are hydrogen donors, bases are hydrogen acceptors. So HCl gives the H plus to NH3, and that leaves it with Cl minus and NH4 plus. The NH3 takes the H plus, and you get NH4 plus. This is going to be a spectator ion, so you can take it out if you want to. All right, so what do we have? We have this amount of HCl provided. So we have 25 milliliters of hydrochloric acid, and so that's 0.025 liters. And we have 0.0320 molar. Okay, so that leaves us with 0.0008 moles of HCl. If it's at the equivalence point, then we're going to have 0.008 moles of the ammonia. And these are both going to get equally reacted with one another. Okay, what's going to form? We're going to get 0.0008 moles of NH4 plus formed. All we need at this point is the total liters. So you can use MV. The amount of ammonia was 1.024 molar. You can use molarity equals moles per liter. You can use MV equals MV. Okay, and then if we use the Thomson switch, that's going to give us our liters of ammonia. This is all for ammonia. And the liters of ammonia, it's 0.000781. So this right here is the total volume when you add these up. And this gives me a total volume of 0.02578, which equals 0.0310 molar NH4 plus. Now, this is an acidic salt. NH4Cl is an acidic salt. This is an acidic cation. If you put this into water, it's going to make H plus. And because this is an acidic cation, we need Ka. And then we can use this shortcut, or we could do an ice table. All right, so if we're provided the Kb for ammonia, you won't always be provided the Ka for NH4 plus. If I'm provided the Kb for ammonia, and I know the Kb for ammonia is 1.8 times 10 to the negative 5, I know the Ka for NH4 plus times the Kb for NH3 equals the Kw. And my Ka, my Kb is 1.8 times 10 to the negative 5. My Kw is 1 times 10 to the negative 14. So this gives me a Ka of 5.56 times 10 to the negative 10. And then using this shortcut right here, the Ka is 5.56 times 10 to the negative 10. And then this equals the x squared over the molarity minus x. We can assume that x is much, much, much less than our concentration of 0.0310. That's what we solved for right here. We're going to assume x is negligible, so we're going to ignore the minus x. Because this is an A, Ka, then our x equals H plus. So plugging in my molarity is 0.0310, and I'm ignoring the minus x. When I solve for x here, you want to cross multiply, take the square root, and this gave me an x of 4.15 times 10 to the negative 6, which equaled my H plus. pH is 10. pH is the negative log of your H plus. So I need to take the negative log of this value, and when I do, I get a pH of 5.38. Okay, so once again, find the moles. These are going to get used up because they're limiting. They're going to tell you the moles formed. Find the liters of the other solution, add them up to get total liters. So moles divided by your total liters is going to give the molarity. Check to see if you're looking at an acidic cation or a basic anion. Then if it's an acidic cation, you need a Ka. If it's a basic anion, you need a Kb. Solve for x. If it's Ka, your x is H plus. If it's Kb, your x is OH minus. And then from there, solve for your pH. Okay, that was the long problem. All right, number 3, when you solve this, you should get, I'm just going to give you the answer so you have it. This one should give you a pH of 7.61. So when you solve this, that's what you should get. Okay, number 4. This is a strong acid, methylamine. Anytime you see something called an amine, that means it's a weak base. Okay, so this is a weak base strong acid titration to the equivalence point. And when you solve for this one, you should get a pH of 5.98. All right, so how do you find an appropriate indicator? Ideally, you want the indicator to have a pKa less than 1 away from your target pH, and that's going to be the pH at the equivalence point. The closer you get to the pH at the equivalence point for that titration, the more appropriate that indicator will be. So, if we look at number 6, so we just did the titration for problem 2. And in problem 2, we said the pH at the equivalence point is 5.38. So ideally, we would like to have an indicator between 4.38 to 6.38. We want it 1 away from the pH at the equivalence point. So I'm going to look at my table. I'm going to find something close to 5.38, and I see methyl red. So methyl red is going to be the most appropriate indicator for this titration. Okay, we look at number 5. Our pH for this was 10.85. And technically, we don't have anything that is a good indicator because we don't have anything that is 9.85 or higher. Phenolphthalein would be the best out of the ones provided, but it's not an ideal type of indicator to use for reaction 1. Okay, so you could put none of the above for this one, for number 5. 7 and 8, you should be able to do those. Okay, now we're going to look at the pH halfway to the equivalence point, and these are a little bit easier. Okay, so here I have my HCN plus my NaOH, and I'm provided with 16 milliliters and I'm just going to show you the long way. This gives me 0.000512 moles. Okay, this is halfway to the equivalence point, so we're only going to use half the number of moles. We're only going to react half the moles of the HCN because it's halfway to the equivalence point. So that means that we're only going to react 0.000256 moles. So I'm only going to add 0.000256 moles of the NaOH. And I'm going to use all 0.00256 moles when I add it to the HCN. So I'm not going to have any of this in excess. Here I'm going to have 0.000256 moles unreacted. This looks long, but they won't all be this long. All right, so in this reaction, we get water plus sodium cyanide formed, and sodium cyanide is the conjugate base of HCN. And how much of this NaCN is formed? We get 0.000256 moles formed. So the amount of HCN that reacted is used to form the NaCN. And because this is a 1-to-1 ratio, the amount of HCN reacted equals the amount of NaCN formed. if we're looking in terms of a limiting reactant. Okay, so this is the long way. If I were to go ahead and find the liters of NaOH, I end up getting 0.0025 liters of NaOH, which gives me a total of 0.0185 liters of NaCN. Well, how many liters of HCN are left over? Because they're in the same solution together, that means I have 0.00256 moles of HCN in a volume, total volume of 0.0185 liters total. Okay, so this is formed and this is left over in excess. It's remaining. Notice these are the same number. So we're going to have the same concentration of our conjugate base formed. So when we divide this, I get 0.0138 molar CN minus. And I'm going to have 0.0138 molar HCN. This is a buffer. We have a weak acid plus its conjugate base present. How much do I have of the buffer? I have equal amounts of the weak acid and the conjugate base. What formula do I use for buffers? I use pH equals the pKa plus the log of my A minus, which is my conjugate base, over my HA, which is my weak acid. So this is the formula we use when we have a weak acid that is forming a buffer by reacting with a strong base. As long as you have some of the acid unreacted present with some of the NaCN formed, you have a buffer. And because we have a buffer, we can use Henderson-Hasselbalch. Okay, so my pH, I need to use the pKa for HCN. And so I need to look at my table and find the Ka for HCN. The Ka for HCN is 6.2 times 10 to the negative 10, which means the pKa is the negative log of the Ka. This is on your formula sheet. And so my pKa, when I take the negative log of this right here, the 6.2 times 10 to the negative 10, this gives me a pKa of 9.21. So the pH equals the pKa, 9.21, plus the log of my conjugate base, which was 0.0138, divided by the concentration of my weak acid, which was the same. Anytime I go halfway to the equivalence point, I'm going to have equal concentrations of my weak acid or base with its conjugate. So the weak substance and its conjugate will have the same concentration. When you divide this, you get 1, and the log of 1 is 0. So anytime you're at halfway to the equivalence point, anytime, the pH equals the pKa. So in this particular problem, the pH equals 9.21. So if I look ahead at number 10, I have my ammonia plus my hydrochloric acid making NH4 plus Cl minus. Acids are hydrogen donors, bases are hydrogen acceptors. This is halfway to the equivalence point. So when you see that it's halfway to the equivalence point, that's a good thing for you because all you need to know is the pH equals the pKa, or if it's a weak base, the pOH equals the pKb. So in this case, I know my NH3 has a Kb of 1.8 times 10 to the negative 5. So my pKb equals the negative log of 1.8 times 10 to the negative 5. And so my pKb is 4.74. The POH equals the pKb at halfway to the equivalence point. So my POH equals 4.74, the pKb. And because the POH is 4.74, and I know the POH plus the pH equals 14, the pH equals 9.26. Okay, just remember that the pH equals the pKa halfway, the POH equals pKb. Use whatever's weak. So here I had a weak base, so I'm using the Kb and the pKb. In this problem, I had a weak acid that was being titrated, so I was using the Ka of the weak acid and the pKa of that weak acid. Okay, so that's how you do halfway to the equivalence point. Number 11, for this one, you should get a pH of 3.14 when you solve. And 12, you should get 10.64. Okay, notice this isn't a mean. That means this is a weak base. Okay, and then the remaining information you need is in the part 2 video.